All right, here's just a quick walkthrough of the notes that I sent with you that will help with the assignment that I gave you, and I'll try and do just a few snapshots of the types of problems you guys have for that homework 12 on WebAssign too. So first off, this is kind of a wrap-up of what we did in class in a little bit tidier fashion, and that's in class. I just wanted to explore this a little bit, see where the spreadsheet plays into it. We'll continue with that again on Wednesday. But this is the basic idea that we have a function where we grow with compounding every n number of times in a year, and all the explanation of what the variables are that we talked about in class are here. And the focus, though, I want to look at just the part between the p and the t. We'll put the p and the t back, but if we play around a little bit, what we found out is if we're going to compound, one thing that I do want to talk is I'm going to kind of take this r out as well, the rate, for just a little bit. So I'm going to pull that out in this context down here. If I just talk about monthly compounding, the idea is that n value, if I say monthly, becomes n is 12, and the result you see there that I circled. If I say daily, then that's 365. The result is what you see there. If we keep going and make larger and larger values and go to infinity, then you actually get this magical number called e. What you can think of is that compounding at the day, by the minute, however often you want to compound. If you do it infinitely, that just means something is growing at a given rate all the time. What that means is continuous growth, and that's nature's way. That's how things actually happen in the real world, is things grow all the time. It's not in spurts. Kids are just exactly that way as they're growing up. It's happening constantly at various times throughout it just never stops. It's not in spurts, though. I should say, with reason, there are definite spurts, and you've all experienced, either seen, witnessed, or been a part of a growth spurt, but you're always growing in that particular age of, pre-adolescence especially. Okay, so the next piece of the sheet it's that idea of continuous growth, natural growth. All things I'm saying are reiterated in this sheet, but the notation that we use, instead of saying to infinity like I notated up above, I actually use this limit as n goes to infinity, and I put n in the function. That's just the notation. It's the same idea, but we really can't do infinity, so we do this idea of a limit, and that's something that we didn't hit on a whole lot in our course. If you took Math 50 or you took Math 70, those are Calc 1 and Calc 2, you would need this knowledge of limits, because it does have applicable situations where it's useful for our purposes. No big deal. Now, down below, what I've done is, what if I put the r back? So here's the r. This is actually more like the function that we saw in class. I had an r in there for the rate of growth. Percentage rate, 5% is the one we used for our example. Well, I took it out just for purposes to do those limits. Well, if I took it out, you'll find that if I put it in a different position, if I take it out and put it out here in the exponent in r, versus having it inside like this, it ends up being one and the same. And the reason I know this is if you run the limit to infinity, both of these end up producing this e to the r function. So it's a little hard to see in here. That's e to the r. So they both give you the result. And so the one that we use, if I can just, again, focus on just the inside piece, I'll try and highlight it. The stuff between the p and the t, right here, and that kind of blurs it out a little bit too much, but that stuff between there is this e to the rn, the one I have on the left, and I'm going to circle that in blue. This right here, this limit that we know is e to the r, that's what you're going to see right inside here. And if I'm really good about my circling, I think I can get it for the most part. That's stuff that you see in there. So we know the limit goes to infinity. That's really just e to the r, that little chunk right there. And then what we're tacking on the ends is multiplied by p, and then to the power of t. So here it is, p e to the r t. And that's the formula that we use for continuous growth, the exponential growth model with continuous growth. We just put in a rate of a given amount. So instead of compounding monthly, daily, or anything like that, we put this is compounding all the time. And that rate, the 0.05 like we used in class, would go in the exponent there. Time, the number of years. When we're doing months and things like that, we would break time up into a different, maybe months amount, and then we do the rate a little bit differently. But again, in principle, it's still the initial amount that you have in there, or how much is in there at the time of, of compounding or applying the rate. All this stuff will clarify, but the idea is that you can see where that particular continuous growth model comes from. It comes from compounding all the time, and you get this magical E number. It's super cool. It has applications in 100 other different places. It's just one of the miracles of nature. We could go on and on again. One of the other cool features of e is that the derivative of e gives you e again. So e to the r, derivative of that would be e to the r with respect to r. There's a little bit more to it, which we'll get to in class. But what we'll notice, this limit idea that I used before, the compounding with the n to the nth power, if that's truly equal to e to the r, then its derivative should also produce the same thing. You know, derivative of e to the r gives you e to the r. And this limit of r, limit as n goes to infinity of 1 plus r over n to the n, which we've found to be equal to this e to the r, compounding all the time. If we take the derivative of it, we should get the same thing. So I've done that. It's a chain rule. And if I take the derivative with respect to r, I pull an n out front, which you're going to see right here. And you take the power down by 1. You leave the inside untouched, and then you times the derivative of the inside. Since it's with respect to r, that's like r over n is the same thing as 1 over n times r, where 1/nth is a constant and r is the variable. And that's what we're taking the derivative of. And then, of course, that means when you do that, you're going to have a dr dt afterward. Dr, I should say, derivative of r with respect to r, but we'll just leave that part off. But that's the derivative. Now, it may look different, but the 1 over n and the n cancel. So really all that's left is this little dude. It is to the n minus 1, but when we're running the limit to infinity, n minus 1 really is still infinity. Infinity minus 1 is still infinity. So we're going to see that basically we take the derivative of both sides, we still get the same function as what we started with. That's one of the big hallmark features of the e exponential function. Now, and the derivatives get slightly more complicated. What I have is that the derivative is always equal to some multiple of the original function. Now down below, we're going to talk a little bit about those exponent rules, and I'll do a couple examples from the homework, and that's it. Now, I'm not going to say anything really much more about these rules as you go through this, but this is a nice summary of everything we talked about in class. They're all there. The idea of distributing a power in multiplication, adding the exponents when you multiply. So these guys right here is power of a power. So if it's x to the m and you do it to the nth power, it's then x to the m times n. Same basis, add them, dividing, you subtract, that type of stuff. So now the biggest thing is, how do I use this in the context of the homework? So let's pull up a couple of those. Okay, here's some quick look at a couple of these problems just to get you kind of rolling. Here's an example of a power to a power. So that would be 3/8, and you want to, because it's power of a power, you'd multiply that times 1/2, the other power. So this would actually be 3 to the 4th. Now you could write 3 to the 4th or simplify and get the actual value itself. You'll have to test WebAssign and kind of see what it goes for. If you need more attempts, let me know. Part D down here, my suggestion is I think distributing that power 3 is more helpful in this situation. So it would be 6 to the negative 3 because I'd multiply them. And it would be 6 to the, now 3 times 2/3 is just 2. So 6 to the 2. Now that's not the end of the story. Now I'm multiplying same bases. That's when I add the exponents. So that would be 6 to the negative 3 plus 2. And then that would be 6 to the negative 1. And finally, that's 1 over 6. So I believe in these two instances, these are the results that would be desirable in C and D. Okay, and then down below, here we're talking about sales in billions. The way this works is we're saying t equals 0 would be 2,000. So to estimate 2013, that'd be t equals 13. You literally just substitute that in here and just very carefully calculate that value. So these are exponential functions. It's just putting the time in the appropriate place. T equals 17, and so on. I think you get the idea. Same kind of thing in this problem where you have, this is 10% over 10 years. It's describing things that you see in this function. There's 10% as the 1.10 cost of goods over a period of a decade. So where P is the present cost, the price and oil change for a car is presently $23.85. So that's your big P that you put in there. Estimate the price 10 years from now, and this is where you do T equals 10 for 10 years from now, and you want to put that in for T. So you're substituting in the 23.85 for P and 10 for T, and getting a result and find out, yeah, how much gas might be in those next, or an oil change in those next couple of years. Flies fast, let me tell you. So anyhow, we have various other functions, same idea. We're going to compound over various amounts of time. So P, and then using 1 plus R over N to the NT. is the type of function that we're using, so you just got to put all the values in the appropriate place, where n is 1, r is 0.06, you want to remember that, t is 60 years, and then you want to use 2500 as your p, your initial amount. For continuous compounding, that changes things, doesn't it? That's when you're going to do p e to the rt, where again p is 2500, and that's e to the r, 0.06, and then t, you're going to do it still over 60 years, so it's still times 60. So this is how you would tackle the continuous part down in the bottom there. Okay, next problem. Oops, sorry, I think we get some dead space in there. I was changing pages, so patiently fast forward through some of that. This is, you're supposed to choose the quantities from the problem that go in here. So if I'm doing $20,000 and a trust fund that pays 4% interest, earned over 50 years, deposit of $20,000, here you are, that's your $20,000, your interest rate 0.04. Your time, you're going to do this for 50 years, and the compounding depends on the type of problem you're going to deal with. This is compounding continuously, and then in this case you want to put infinity. Use the symbol box over to the left to do that, and the appropriate formula for that is the top one. So using that, if you put in that p, r, and t into that function here, you're going to get a value, and that's what you'll do for the result of that one. That's the end of the story. Should get you through most of the homework, and then email with questions on the rest. Again, sorry for the dead space in there. I'll warn you in the email. That was me changing pages. I have the option to pause, and I forgot to do that. Take care.